Today's video covers Green's theorem, so we're going to continue with line integrals. Before this, we've calculated line integrals, we've looked at the applications. Main application of a line integral that we've been looking at is calculating work. The other two applications that we've seen of line integrals, we can use a line integral to calculate the mass of a wire that is shaped like our curve C, or we can also use a line integral to calculate the area underneath some curve. After we looked at line integrals, we looked at the fundamental theorem of line integrals. So that told us if we have a vector field, we're calculating work, and if that vector field is conservative, then we can use the potential function to calculate work. Well, today we're going to look at another way to calculate line integrals, and that is Green's theorem. So before we even talk about what is Green's theorem, Green deserves a little bit of our respect, so let's take a few seconds to learn about him. This is a photo of George Green. He was alive 1793 to 1841. So as you can see, he was a British mathematician and a physicist. He was actually self-taught. He only had 1 year of formal schooling. His father was a baker. And what's kind of sad is his work really wasn't known until after his death. So today, we're going to look at some of the work that he has done, or that he did. Okay, so as we can see over here on the right, Green's theorem, let R be a simply connected region whose boundary is a simple, closed, piecewise, smooth curve oriented counterclockwise. So that's really important. In order to use Green's theorem, you have to have a simple, closed region, and your curve has to be oriented counterclockwise. And so we can see the orientation on our curve here. Oh, I went backwards. So that counterclockwise, that tells us that we have a positive orientation. The way that you can tell that an orientation is positive is the region is on the left as you travel around it. So if you picture here and you're moving around the region, like you're walking around it, you can see the region would be on your left. So that is our setup. So then, if f of xy and g of xy are continuous and have continuous first partials on some open set containing R, then the line integral of f of xy dx add g of xy dy is the double integral over the region R of the partial of g with respect to x subtract the partial of f with respect to y dA. So what I want us to notice is this is a different setup, a different line integral than when we calculated work. When we calculated work and we used the fundamental theorem of line integrals when we were able to, when we had a vector field that was conservative, we had the line integral of f dot dr. That's not what we have here. Okay, so we would use Green's theorem in a different case than when we would use the fundamental theorem of calculus. So before we get into actually using these theorems, let's do a proof, right? We haven't proved anything in a while, so let's prove Green's theorem. So we're going to start with, we have a simple, closed, piecewise curve that is oriented counterclockwise. So maybe we have something like this, and it is bound on the left, and it's bound on the right. And maybe the bottom of this curve we can write as a function of x, and the top of this curve we can write as a function of x. And it's oriented counterclockwise. Or we could have something that looks like this instead. Maybe it's a similar idea, but it's bound on the top and bottom. And we can write the left side of the function as a function of y, and the right side of this curve as a function of y. And again, it is oriented counterclockwise. So here's what we need to show. First, we need to show that the line integral of f of xy dx is equal to the double integral over the region R of the opposite of the partial of f with respect to y dA And then we need to show that the line integral of g of xy dy is equal to the double integral over the region R of partial of g rather, with respect to x dA. And this goes back to Green's theorem above, right? F of xy dx gives us the negative partial of f with respect to y. G of xy dy gives us the partial of g with respect to x. So we're going to start by proving one, and then we'll prove the second statement. There's some more room on the next page of these notes where you can continue your proof. So what we are going to say is we are going to prove 1, and we are going to let C1 and C2 be boundary curves. So we're going to, just to give ourselves a visual, say that our curve looks something like this, and the bottom is curve C1 and the top is curve C2. So then we're calculating the line integral of f of xy dx. That can be written as the line integral over curve 1 of f of xy dx, add the line integral over to curve 2 of f of xy dx. Now, the issue here is that these curves are going in different directions, right? Curve 1 is going from left to right, curve 2 is going from right to left. We want them to go the same direction. So what we're going to do is we're going to rewrite this one so that they're going in the same direction. So we want both curves to go left to right. And so if you remember from a previous set of notes, if we reverse the orientation of the curve, what's going to end up happening is we get the reversed sign of the line integral. And then the first one's just going to stay the same. Okay, so now at this point, let's parameterize. Our curve C1, I'm going to call xt, and y is some function of t. And then our curve 2, x again is going to be t, and y again is going to be some function of t. And this is just following the picture that's on the previous page. So then what happens is this line integral of f of xy dx, if we calculate this using our parameterization, or we rewrite using our parameterization, t is going from a to b, and we have f of t, g of 1t, dt, subtract a to b, because we reverse directions, so now our bounds on t are the same, f of t, g2 of t, dt. So then I take out a negative from a to b, and this will give me f of t, g2 of t, dt, subtract f of t, g1 of t, dt. So all I did was take these terms and reverse the order. So this one now goes first because I factor out a negative. That one goes second. So this then gives me negative from a to b. It's the function f t comma y, where y goes from g1 of t to g2 of t, dt. Oh, we're going to run out of room. Hopefully you used your room more wisely than I did. I'm going to keep going, so you might have to find yourself some extra room. Okay, so what I did is I took these functions and I just gave them the variable of y so that I can say y is being evaluated between these two values. And the reason I would do this then is I can now write this as a double integral. So the outer integral is still a to b. The integral the inner integral, y is going from g1 of t to g2 of t. And then we have the partial of f with respect to y, dy dt. So you should be asking yourself, why is this a partial of f? Well, if I have to integrate twice, if I integrate partial of f with respect to y, I'm going to get back to f. Right, so I have to integrate with respect to y first so that I can evaluate y, and then my outer integral is going to be t. Okay, so finally, when did we introduce this t? Well, t is really just x. So really what this is that dt is really dx. So finally, this becomes negative double integral over the region R of the partial of f with respect to y dA. dA. And it's similar for g. So that was really only half of Green's theorem that we proved. We didn't prove the second half. I'm not going to, but it's the same general idea that you can see. So now that we've proved Green's theorem, let's actually use it. Example 1, we're going to calculate that integral, line integral, where c is as below, and then we're also going to find f dot dr. Okay, so first of all, you don't have c, so let's draw Cn. C goes from 0, 0 to the point 1, 1. And we have the line y equals x, and then we have the curve y equals x cubed. And we travel y equals x cubed first, and then y equals x. Okay, so first thing, we look at our line integral, and we have something dx, something dy. So when we see that, immediately in our mind, we should be asking ourselves, can we use Green's theorem? In order to use Green's theorem, there's two pieces that must be true. First, our curve must be closed, and that is true. Secondly, we have to be oriented counterclockwise. And so as we're moving around, the surface should be on our left, so that's true. So yes, we can use Green's theorem. So what that means is this line integral is going to turn into a double integral over the region R, where we take the partial of g with respect to x, subtract the partial of f with respect to y, and then dA. Okay, so I'm going to figure out the bounds in a minute. Partial of x with respect to, partial of g with respect to x, is this one. So with respect to x, that's going to be 3x squared, add 3y squared. Partial of f with respect to y, so that one, so we're subtracting 3y squared over the region R. So there's a dA here. So this just becomes 3x squared. So then we have to determine, are we going to integrate with respect to x or y first? Based on the region, because we have two functions of x, I'm going to integrate with respect to y and then x. Y goes from x cubed to x. X goes from 0 to 1. Okay, so then if we're ready to integrating with respect to y, I get 3x squared y from y equals x cubed to y equals x. So that gives me then 3x cubed, subtract 3x to the 5th. And then when I integrate and evaluate again, I get 1/4. So that was the first part of the question. We also have to calculate the line integral of f dot dr. Now, before we jump in and do too many calculations, one thing that I want you to notice is that f, the vector field, has components y cubed and x cubed plus 3xy squared. Okay, so that is our f. dr then, if we think about dr, that's the partial with respect to x of the first component, aka dx, the partial with respect to the second component, partial with respect to y of the second component, aka dy, So this f dot dr is really just a different way of writing this line integral. So we already got that. It's 1/4. Okay, so this is going to lead us on next to some common notation. Okay, so if we have a closed path, then let's say if you're asked for the line integral, like we just were, of f of xy dx plus g of xy dy, oftentimes if you have a closed path, it'll be indicated like that. So that little circle tells you that it's a closed path, which then we can use Green's theorem right away. Double integral of partial of g with respect to x, subtract partial of f with respect to y, dA. Sometimes what will even be used is you'll have the line integral, you'll have c, and you'll have that circle. And sometimes, if you're really lucky, you'll be given this symbol, which tells you the orientation. So now we know that we are oriented counterclockwise. And then another fun fact for us, if our vector field is conservative, then f dot dr around a closed region is going to be 0. And we actually saw that before when we did the fundamental theorem of line integrals. We saw that if we had a conservative vector field and then we had a closed figure, if you remember, the starting point and ending point, as long as they were the same, you could take any path. Well, in this case, we're starting and ending at the same point, so we can just say we didn't move, we stayed in the same point. Okay, next thing, another application of Green's theorem. So we've looked at before that we can use a double integral to calculate area. We can also, though, do this as a line integral of x dy, which is the same as the line integral of negative y dx, or we can do 1/2 the line integral of negative y dx add x dy. So any of those will calculate area as well. So let's see an example of that. Use a line integral to find the area of that function. Okay, so hopefully looking at this, you know that we have an ellipse. And if we draw ourselves just a quick sketch, we have an ellipse where the y value is going up to b and down to negative b, and x is going between negative a and positive a. So one way we can calculate area using the options above is a line integral of x dy. Well, we're going to need to parameterize that curve. And so maybe you remember this from before. X can be written as a cosine of t, and y can be written as b sine of t, and that is for t between 0 and 2 pi. So rather than setting this up as a double integral, we can just have a single integral. So this will be the integral from 0 to 2 pi. Our x is a cosine t. If we take the derivative of y, we're going to get b cosine t dt. And that's it. That's all we're calculating. Okay, so pull out a, b, because those are constants. And we're going to get cosine squared of t dt. And then maybe you remember from an earlier video, I reviewed the trig substitution for cosine squared of t, which is 1/2. Add 1/2 cosine of 2t dt. And now we're ready to integrate. So this is ab multiplied by 1/2 of t, add 1/4 sine of 2t, being evaluated from 0 to 2 pi. And so finally, our area is pi multiplied by ab. So this example just shows you that you can calculate area using a double integral. You can also use a line integral. So sometimes a double integral is easier, sometimes the line integral is easier. Okay, we got a few more things before these notes are done. Next thing that we are going to talk about is multiply connected regions. So what's happening here is, let's say you're a point on C1. You're going to go along, and at some point you're going to move in, you're going to go around that C2, you're going to go back, and then you're going to keep going. So again, you start on C1, you get to a certain point, you go in, you travel C2, you come back, and then you keep going around. Okay, so how do we calculate the line integral there? We're first looking at that outside curve. I don't think I gave myself enough space there. That is going to be the line integral of C1 of f of xy dx add g of xy dy. So that's going to take us around the entire figure. Well, what happens then when we stop and we go in? What does that contribute? Well, we have to think we're going to go in and then we're going to exit. So that actually contributes nothing. So then we have to look at that curve 2 instead. And what I want you to notice is that that curve 2 is clockwise. It's not counterclockwise. It's clockwise, not counterclockwise, so we would need to reverse the orientation. Okay, so we would also have this for our second curve. And if we were using Green's theorem, what this would become then, we would have double integral over the region R, so this is for the first line integral, and we would have the partial of g with respect to x, subtract the partial of f with respect to y dA, exactly like you would expect. But then for that inner piece, so that second integral right here where we need to reverse the orientation, it's going to be the partial of f with respect to y, subtract the partial of g with respect to x dA. And so because we reversed the order, we applied a negative, that we would now be going counterclockwise instead of clockwise. Okay, so this leads us to the question of what happens if a curve has a negative orientation. So that's going to be our last example. So can we use Green's theorem if we have a negative or a clockwise orientation? So we are going to evaluate this line integral where C is the triangle curve consisting of the line segments from 0, 0 to 0, 1 to 1, 0, and then back to 0, 0. Okay, so if we draw this, we're going from 0, 0 to 0, 1. And then we are going to 1, 0. And then we are going back to 0, 0. Okay, so we can see that this has a negative or a clockwise orientation. So we can't use Green's theorem yet. We need the curve to have the reverse orientation. Then we could use Green's. So what we're going to do a double integral. If we reverse the orientation, it's going to give us a negative value. So then, okay, partial with respect to x is going to be y. Partial with respect to y is going to be 0. So ultimately it would be negative double integral of y dA. Really, there shouldn't be a label here. It's just the region R. So yes, if you have a negative orientation or a clockwise orientation, you can use Green's theorem just by reversing the orientation. Okay, so this was Green's theorem. What is most important with Green's theorem, if you're going to use it? First of all, that it's the right type of line integral. It has to be some function dx at another function dy. And what you need to make sure, not only do you have a positive or a counterclockwise orientation, but remember the curve also has to be closed. And if so, you can take that line integral, put it into a double integral. Next video doesn't have line integrals in it. So, woohoo, we get a little bit of a break. Next video is on divergence and curl. So, until next time.